Section 4 is exponential functions, not logarithmic functions. But before we get into exponential functions, let's take a look at the graph of the natural log of x. We've seen this before. We did it in like section 1 or something. Maybe it was section 2. No, section 1, wasn't it? Yeah. So here's our graph of the natural log of x. From what we just learned about inverses, what can we say? There's some stuff we can say here. No, that's not what we learned in section 3. From section 3, what can we say? Why can we say that there's an inverse? So our vocab word for that is, right, this thing is monotonic. It's always increasing. And because it's always increasing, and it is continuous, we can say that there is an inverse. Now, if I was to try to graph the inverse of the natural log of x, no. I'm just trying to graph the inverse of the natural log of x. Using a graph, how would I go about doing that? Graph a little line, y equals x. So, yeah, I'm actually asking you very primitively, how can I graph the inverse using a graph? So there's a line y equals x. That's a line. Now what do? Reflect points across that line. So right here I'll reflect that directly. It has to go perpendicular into that reflection line and then continue on the same distance. So here it looks like I'm maybe like 1/2, so I'll go there. Here, maybe there, and so on. So here, perpendicular in, that's going to be a weird one. Maybe there. 7, 2. Yeah, that one's going to be way up here or something, right? That's probably too far. Maybe about there. Okay, over here, because this does continue this way, so this will continue to reflect this way. Like that. Pretty close to that 2, so pretty close to that 2. Looks like right on that 3, so I'll put it right on that 3, and then we kind of do this. So the graph that I've created seems like it has a horizontal asymptote, and then it just takes off. There's your inverse graph of the natural log of x. What does that look like? It is e to the x. So here we are. The graph of e to the x is here officially, graphed by a computer. And the graph of the natural log of x was here. The graph of y equals x is here. And we can see that this is a reflection in the line y equals x. So since the function y equals the natural log of x is always increasing, and it's 1-to-1, it doesn't do something like that. It's monotonic. It has an inverse. The graph is a reflection across the line y equals x. This reflection precisely produces the graph of y equals e to the x. Therefore, the two functions are inverses. And because they're inverses, when I compose one of the other, which is what's going on here and here, f composed of g and g composed of f, when I compose them of each other, I get x because they're inverses of each other. Okay? So you can think of this as e to the natural log undoes each other. They disappear. The natural log of e undoes each other. They disappear. So think of properties as undoing each other, just like other functions and operators undo each other, like multiplication undoes division. Addition undoes subtraction. Squaring undoes square roots. Cubing undoes cube roots. Inverse trig functions undo trig functions. And the natural exponential function undoes the natural logarithm function. Undoes? I have no idea. Sure, why not? I mean, to do is a verb, right? So to undo seems like it should be a verb. And then you would think that undoes, therefore, is a word. you can convert any equation from one form to the other. So from exponential form to logarithmic form by applying the correct function to either side. So for example, solve this equation right here. In order to solve this equation, I got to somehow get that x out of the exponent. In order to do that, I can undo e by applying the natural log to both sides. So now I have the natural log of 7 equals the natural log of e to the x plus 1. These undo each other, and I'm left with the natural log of 7 equals x plus 1. And now I can solve for x. The natural log of 7 minus 1 equals x. On this one, what do we need to do? We're not timesing. This is not multiplication. This is applying e to both sides. Okay? Both sides then become an exponent of e. E to the natural log of something wipes out e and natural log, and I'm left with the 2x minus 3 equals e to the 5th power. Okay, just solve for x now. So I add 3 to both sides. 2x equals e to the 5th plus 3. Divide both sides by 2, and I get x equals e to the 5th plus 3 divided by 2. That'd be the exact answer. Now, on the calculator, you can do that, and you'll get an approximation. And again, the approximation should be to 3 decimal places, and you never want to do an approximation until the very, very end. So let's see if we can get an approximation for this one. $75.7067. So 7. There's your answer. Okay, the usual rules of exponents still apply to natural exponential functions. If I have like bases, I add the exponents. So e to the a times e to the b becomes e to the a plus b. We use this one a lot. E to the a divided by e to the b, those are like bases, so we subtract the exponents, and we use this one a lot as well. So you need to remember those. Remember that e is a base, just like x or y or 2. Remember the interesting property of y equals e to the x. We learned that before we even started this chapter. It is its own derivative. We kind of showed that, and we almost even derived e on our own just by graphing, and then using a delta x of increasingly smaller and smaller values. So we actually figured this out, this rule out on our own. That's what e to the x is. That's why it's special. It is its own derivative. So the derivative of e to the x is e to the x, which means that the derivative, using the chain rule of e to the u, if I put some function in the exponent, I use the chain rule. I call the exponent u, and the derivative becomes e to the u times the derivative of the exponent. This is a fantastic rule right here, and it makes taking the derivative involving e to the something very easy. So let's take the derivative of e to the 2x minus 1. That's not just e to the x. The derivative of e to the x is pretty boring. It's just e to the x, so there's no point in doing that one. The derivative of e to the 2x minus 1, though, that one is interesting. So what we're going to do is let u equal 2x minus 1. And then we are taking the derivative, so u prime equals 2. The chain rule says the derivative of e to the u is e to the u times u prime. So therefore, this derivative becomes e to the 2x minus 1 times u prime, which is 2. So the answer I'm going to write is 2e to the 2x minus 1, and I'm done. So how about one that looks like this? The derivative of e to the negative 3 divided by x. Let u equal negative 3 over x. Which is negative 3x to the negative first power. Good. Remember, we're taking the derivative, which means the exponent decreases by 1. It kind of seems like there might be a natural log situation here, but we're taking the derivative. We're not integrating. So the negative 1 comes down and becomes positive 3x to the negative second power, which makes it 3 over x squared. So now we can take the derivative. What do we get? Times u prime. 3 over x squared. Are we done? We can write this in a little bit simpler form. We can write this as 3 e to the negative 3 over x, all divided by x squared. There's your answer.